Welcome to Microlecture 15, Comparing Acid-Base Reactions. Here we use all of the information that you've learned so far to solve a few problems. Okay, so the question here asks, what is the strongest acid and why? And so for a complete answer, it would have to include the reason why. So there's a couple of different protons circled here, and so that's just a hint that, when we're coming up with the conjugate base, that we're abstracting the proton that's indicated. So I'm just going to do the same process for each of these and come up with the conjugate base in both cases. Remember, our strategy is to determine which conjugate base is more stable, and then we will reason that that's the conjugate base that will form most likely, meaning it came from the strongest acid. Okay, so when the nitrogen loses its proton there, we get this as a conjugate base, and for the other possible acid, everything looks very similar except this is a carbon-carbon double bond instead of a carbon-oxygen double bond as in the other option here. And so again, we're just asking which is more stable. There's lots of factors that can contribute to stability, but resonance is definitely one of the most common ones, and we have red flags for resonance here. So we're going to consider resonance, and I can see this resonance form for sure that could form. In addition to that resonance form, we have another one. And if that arrow pushing seems strange, you could have also gotten there by going the other way on the original structure. So there's another resonance form that can be drawn here. So lots of stabilizing force here. If we do the same kind of process on the other side, what we learn is, well, yeah, we can kick the electrons up this way and generate the same sort of resonance form that we did in the other possibility. But when it comes time to look at the other resonance form, well, that resonance form is a very minor resonance contributor. Alright, and so because this is such a minor resonance contributor, the conjugate base on this side is indeed more stable, and therefore it came from a more acidic species. Okay, in other words, this proton is much more likely to be abstracted than the one that we're comparing with. Okay, and the next question we're asking, which of the following is the most acidic proton? So it's going to be important to go ahead and draw in all of the protons. There's these 4 on the benzene ring. We know there's 3 sitting right here, and then there's a couple of more right here. So hopefully you were able to find all of those, and you know, these 2 are pretty much identical, and these 3 are pretty much identical, so it doesn't matter which one of those you abstract, and that greatly reduces the number of possibilities you have to draw through as you're drawing out. Hopefully you're doodling all these possibilities. What you'll find is that, you know, trying to abstract a proton directly off of the benzene ring, that's going to give a negative charge to one of these carbons that I've dotted in red, and that's really going to get you nowhere in terms of stability or resonance. We're putting a negative charge on an sp2 hybridized carbon, so this isn't going to give us a very stable conjugate base for sure. And so that leaves us with either the option of abstracting a proton here and kicking the electrons onto this carbon, and right away I'm seeing that there's some resonance there, or abstracting one of these protons and kicking the electrons off onto that carbon. And here I'm going to guess that there's more resonance, because not only am I going to be able to have the resonance that the other position did through the benzene ring, but I've also got the ability to delocalize these electrons through the nitro group as well. So I do recommend that you draw this out and convince yourselves that it's true, but this is the most stable possible conjugate base that you could form. And therefore, these are the most acidic protons, and I'll go ahead and highlight them in green. Okay. So those are definitely the most acidic ones, but it would take some drawings to support your answer. So it says and why. We can answer that with both words and drawings, and in this case we would want to draw out all the possible resonance contributors. So there are many. If we push the electrons through the nitro group, we end up with something like that as a resonance form. And then, of course, there was the other option of pushing the electrons the other way and kicking them off onto a carbon atom in the benzene ring and resonating throughout the benzene ring. So there's more forms than just what I have drawn here, certainly. Okay, and more. So because we can draw so many different resonance forms, again, that's why one of these 2 protons is the most likely to be abstracted and are the most acidic. And then last example here, we need to show curved arrow mechanism for this acid-base reaction. and predict the favored direction. So I'm going to go ahead and draw in the most acidic proton. Here we can clearly see that that's the one that's abstracted when we look at the product that's being formed. And so if we take the negatively charged carbon, the electrons on it, we can form a bond to hydrogen, kick the electrons off onto the carbon, and we end up with the structures that are shown on the right-hand side. As far as which direction is favored, we usually look to the stability of the conjugate bases, right? So I'm going to reason that this is a stable conjugate base compared to the other one because of resonance. Okay, and so I've got resonance stabilization there. There's one resonance form that can form. And then we could have gone the other way as well, with the electrons around the other way around the ring. So comparing that to this situation, there's no resonance at all. No resonance opportunity. It's a localized negative charge. This reaction is going to favor the forward direction so that we can form something that is more stable. Reactions, again, go from strong to weak, and more stable means weak.